Hi, I'm Matthias Beck, and in this video we will finish chapter 12. We'll give a version of Euler-Mclaren summation in d dimensions. Let me remind you of the Todd operator. Here's the definition again. This is essentially the generating function of the Bernoulli numbers, but we have a differential operator. I'm also reminding you of a sort of multivariate Todd operator where we have m variables. And on the right you see sort of the fundamental lemma on the Todd operator, namely what happens when we apply it to an exponential function. And this gave rise to the Euler-Mclaren summation. So as you will see now, this is a one-dimensional version of something that we will prove in higher dimensions. Namely, if we integrate the exponential function over an interval from a to b and perturb this by some variable h1 and h2, then the Todd operator in those variables h1 and h2 will transform this integral into an exponential sum that you see here on the right, and we think of this as an exponential version of an integer point transform. We already remarked that this is sort of a way of seeing the one-dimensional polytope interval from a to b and the relation of its continuous integer point transform, namely this integral that you see on the left, to its discrete integer point transform that you see on the right. In both cases, we use an exponential variable. And you can think of these perturbation variables, h1 and h2, as perturbing the endpoints of our interval. So in one dimension, those are the facets of my one-dimensional polytope. And so the higher dimensional Euler-Mclaren phenomenon gives now the analog for a d-dimensional polytope. So here it is. So we have a polytope given by a system of linear inequalities, ax less than or equal to b. And what we're doing is we adding sort of a perturbation variable. So this is now an m-dimensional variable if we have m facets. And the original polytope p is given when my perturbation vector is the zero vector. If you think of the system of inequalities as describing one facet per row, then each component of h will give you the perturbation of that facet. And since we're moving the right-hand side, we're sort of doing parallel shifts of this facet. We think of h as a small vector, and so the theorem that you see here, the Khovanskii-Pukhlikov Theorem, gives you now the analog of the one-dimensional Euler-Mclaren summation. So maybe let's look at the statement first. Just like in one dimension, what we're doing is we're integrating an exponential over this perturbed polytope, then apply the Todd operator in as many variables as we have facets, and afterwards we're setting these perturbation variables equal to 0, and you will get the integer point transform of p in an exponential variable. In the version that we're giving here is I need to assume that my polytope is unimodular. So let me tell you what this means. So we know the vertex cones of p, and p being unimodular means that each vertex cone is unimodular. Philosophically, we have a lattice polytope, and if you now stand at any vertex and consider the vertex cone, this vertex cone is generated by a z basis of z to the d. So this implies in particular that not only is p a lattice polytope, but it's also simple. At any rate, so from this Euler-Mclaren formula, you get a special case for the lattice point count. So this is the special evaluation when all the z variables are 0, because then we're plugging the vector 1, 1, 1 into the integer point transform. And on the right-hand side, if z is equal to 0, we're just integrating the constant function 1. And so this integral is the volume. This is a special case of the more general formula that you see on the bottom of this page. So let me give you an idea how to prove the Khovanskii-Pukhlikov formula. We'll start with the continuous version of Brion's theorem. I remind you of its statement over here. And the first remark is that if P is unimodular, then what we had over here, if you remember, these are the generators of the vertex cone at V. If you have a unimodular polytope, then these generators form a lattice basis, and so the absolute value of the determinant is 1. I should also tell you that this continuous version of Brion's theorem, we assume that we have a simple polytope, and so again, this is automatic if P is unimodular. At any rate, so the Khovanskii-Pukhlikov formula starts with the integral over this perturbed polytope, and so the first thing we should do is realize what happens with the vertices. So let's say my old vertex, V, now gets perturbed. And so let me write this as sort of depending on the generators of the vertex cone. So we have some perturbation factor depending on each generator. And of course, this perturbation factor will also depend on the vertex that I'm considering. So the philosophy here is I'm perturbing the facets of my polytope, and this perturbation has an effect on the vertices, and I can describe that effect by telling you how each vertex gets moved in terms of the generators of the vertex cone at V. Now you can convince yourself that if the perturbation vector is small enough, then our polytope remains simple, and so I can use the continuous Brion theorem. The generators are still the way they were before, so the only thing that changes is this first exponential. So instead of V now I have this perturbed vertex, and I can write down the perturbation effect like so. And I have to take the dot product of this with Z. Again, my generators stay the same, so this determinant is still 1. And the same thing on the bottom, so my generators are still the same. And now you can see, so we really need to study what happens in the numerator over here. So this exponential can be picked apart. So we have the exponential function of v dot z, and then the exponential of a sum becomes a product of exponentials. So we have a product of the exponential function negative h times the direction vector w dot z. And now what's going to happen is we apply the Todd operator in this multivariate parameter h. And so the Todd operator, the only place where h appears is over here. And so we will apply the Todd operator only over here. And now you can see we'll be able to use our very basic lemma of how the Todd operator acts on simple exponential function. So here's where we are. We have on the left-hand side our integral over the perturbed polytope. We apply the dot operator, and I just copied the right-hand side and pulled the dot operator to the place where it actually gets applied. And so what we have here is we have the h variables over here. And then this dot product over here is independent of h. So we're precisely in the form where we can apply our basic lemma, how the dot operator acts on an exponential. This means that this expression over here equals, well, first we have a negative wj dot z, and then we have an exponential of the kind that you see up on top, divided by 1 minus e to the wj dot z. There's two minus signs now, and they cancel each other. Okay, we're almost there. I'm reminding you that at the end of the day, we're going to set all variables equal to 0. And so the effect this has is this here becomes 1. So this is just copied from the previous page, and we see a lot of things simplify. So the minus 1 to the d goes away, and we have these dot products of wj dot z. They cancel. And so what remains is this exponential v dot z. And these terms, 1 minus e to the generators. But now we will use one more time the Brion theorem in its original form, because what we see on the right-hand side are precisely the integer point transforms of the vertex cones. Remember, my vertex cones are unimodular, and so this is the integer point transform in an exponential variable. And this is what the Khovanskii-Pukhlikov theorem claimed.